In this lecture, we will learn about debugging C# code using Unity and Visual Studio. This lecture is important because it may introduce you to some of the techniques you haven't yet been exposed to if you're a beginner programmer. These approaches include analyzing the stack trace and printing out or logging values to the console. The first approach we will look at is examining the stack trace. When your code throws a runtime error, a stack trace will be printed that shows all of the method calls leading up to the error being thrown. To see the stack trace in Unity, click on an error message to select it and look at the window below it. When I say stack trace, remember that a stack is a programming data type that follows the principle of LIFO, last in, first out. For any beginner programmers that may not know what it is, this just means that the last item added to a stack will be the first item out of the stack. So in this case, printouts at the top of the stack trace are more recent than those at the bottom of the stack trace. The next approach we will look at is printing out values to the console. Following what values are assigned to which variables and how they are changing during execution of the program is important in the process of debugging. You can print out values to the console and see if any of the values are different than you expected. This helps you to narrow down which part of the code is problematic. To print out these values to the console, you can use Unity's debug log function. This function lets us print out statements to the Unity console. There are other variants of this statement, including debug.log warning and debug.log error, that let us print out our own custom warnings and errors to the Unity console. Another debugging approach is to run the code in debug mode and to add in breakpoints. Debug mode is a feature of MonoDevelop and other development environments that lets us pause the execution of our code while it is running and examine the values of variables in real time. It is a very powerful technique, and all developers should know how to use it. Breakpoints allow you to pause the execution of your code on certain lines and trace the flow of execution. They are great for letting you specify where to pause the code, and for allowing you to see exactly what lines of code are executed at what time during code execution. Another way to debug your code is to comment out potentially problematic code. If your code is throwing an error, you can comment out suspicious lines to see if the error still occurs without those lines. If it doesn't, obviously the code you commented out is causing an issue. To comment out code in MonoDevelop, you can use the following preset hotkeys. On a Windows machine, highlight the line or lines of code you want to comment out, and then hit Ctrl-Alt-C. On a Mac, highlight the lines, and then hit Command/. A stack trace is information logged to the console when an error occurs. It shows the function calls leading up to an error being thrown. To see a stack trace in Unity, click on an error message to select it, and then look below it to see all of the function calls made leading up to that error. Remember, stacks use the principle of LIFO, last in, first out, so printouts at the top of the stack trace are more recent than those at the bottom. In order to properly examine a stack trace, you need to have an understanding of the different information being shown. In the stack trace shown here, the first line includes the error name and description. The second line tells us that the issue is happening on line 24 of the gamelogic.cs script inside of the getObjectName function. The next line of the stack trace shows us the line where the getObjectName function is being called from. Thanks to this line of the stack trace, we learn that the getObjectName function is called on line 20 of the gamelogic.cs script inside of the printObjectName function. Finally, we learn that the printObjectName function is called on line 11 of the gameLogic script in the start function. Remember, the last line of the stack trace is the one called first, so the progression here is that within the start function, the printObjectName function was called. From within the printObjectName function, the getObjectName function was called, and within that function is where our error is. Specifically, line 24 seems to be the problematic line, since it is the line given in the stack trace. Usually the line shown is where the error is occurring, but it could be off by a line or two. This diagram breaks down the same stack trace and points out the main parts. The root cause of the error is shown in the error message logged to the console, where we are shown the location of the script and the approximate line number where the error occurred. In this case, our script is located inside of the assets folder, and the line number given is 24. On the left-hand side of each line in the stack trace are the script and function names, and then the location of the scripts in our project in parentheses, and finally the line numbers so we can see the lines leading up to the error being thrown. Let's jump to Unity and see a hands-on example. To get started, we will open up the scene and script in the example 1 resource attached to this lecture. As you can see by looking at the script, if we hit the spacebar, a sequence of function calls happen one after the other. Let's go to the editor, hit play, and hit the spacebar. As you can see, a series of log statements were printed to the console. Going to the bottom of the console, click on the last printout, the ammo count being 95, and you will see a stack trace pop up. You can see that first, the code in the update function was executed. Next, the player shot weapon function was called, which then called the load function. Next, the aim function was called, followed by the fire function. Finally, the ammo count -5 was printed out to show that the player only has 95 bullets remaining. Essentially, what we just looked at was how to follow a stack trace. In a similar way, some errors are printed out with a stack trace, and you would go about understanding them in the same way, looking at the trail of function calls leading up to the error. It is important that you understand the built-in classes that Unity provides. Think of these as tools Unity provides you, so that you don't have to reinvent the wheel or do everything from the ground up. Unity gives us the debug class, which is filled with functions to help us debug our code. Check out the link to the Unity documentation on this class attached to this lecture as a resource. We will look at snippets of the documentation during this lecture. Let's take a look at the debug class's documentation. Unity's documentation is structured in the following format. First come the class name, then a description of the class, then properties or variables that you can access, and then functions that you can access. One key note is that in order to access static variables, you need to reference the name of the class, then use the dot operator, and then type the variable name. Next up, you will see all of the methods that this class provides us. Remember, you will need to add parentheses and possibly arguments at the end of the function calls. The functions we will cover in this lecture are break, drawLine, log, log error, and log warning. Break allows us to pause the editor during execution and inspect the values of our variables. drawLine allows us to draw a line in the scene view between 2 points that we specify. Log, log warning, and log error allow us to log a message, warning, and error to Unity respectively. Using these functions allows us to customize our output to the Unity console. The debug log function allows us to log or print output to the Unity console. For example, debug log hello world will print hello world to the console. Here we can see this statement, and the result is output to the Unity console. The debug log function is very useful when debugging, because it allows us to print out the value of variables at certain points in our code, and also lets us put in log statements to see what parts of the code are executing. There are many variations of debug log, 2 of which are debug log warning and debug log error. Debug log warning lets us log a custom warning to the Unity console. Notice that the yellow triangle is printed out to the Unity console, just like the warnings that we see from time to time in Unity. Debug log error logs an error to the console. Notice in this example how the red error symbol is logged to the Unity console, with the message we specified as a string. Another strength of debug log statements is that they support rich text, similar to CSS, which allows us the additional customization of controlling the color and style of our log statements. We can print colored output, bolded output, and italicized output. We can also combine these, for example, printing out our output both in color and bolded, for example. Let's jump to Unity and get some hands-on practice using debug log statements. We will go into the example 2 resource file attached to this lecture. First, open up the debug log script by double-clicking on it. Here we have several examples of using debug log and a few of its variations. Debug log this is a message is how we log a traditional message to the console as output. This will most likely be the debug log function that you will use most in your project. It is the traditional way of printing output to the console. The next example, debug log warning, this is a warning, outputs a custom warning to the console. If you want to throw a custom error, you use the debug log error function. Debug log error this is an error will log the custom error with the text this is an error to the console. The next 3 examples use rich text, which allows us to print colorful and stylized output to the console. Notice how color tags are used in all three examples. Using the B and I tags allows us to show the text in bold and italics respectively. Let's minimize Visual Studio and go back to Unity. Open up the Unity scene for this example, and then hit the play button. When we go to the console, you will see that 6 log statements were printed out. The first is the message. The second is the warning. The third is the error. The fourth is the blue text that we used the color tag with a value of blue to print out. The fifth printout was made using the red color tag and the bold style tag. The sixth printout is the result of combining the use of the color tag with a value of green and the italicized style tag. And there you have it. That's how you customize and log console output. Never overlook the power of using log statements when debugging to see what parts of your code are being hit. Debug drawLine allows you to draw a line in the scene view. You supply it the start and end points and other optional parameters. Here's a snippet of the Unity documentation on the function. The first argument you supply the function is a vector 3 of the starting point, the point in world space where the line should start. Next, you specify the end also as a vector 3. These two arguments of start and end are the only required arguments. Additionally, there are 3 optional arguments we can pass into the function to customize it further. We can pass in a color to make the line a color other than the default color of white. The duration can be specified to tell Unity how long the line should be visible for. The depth test argument is a boolean with a default value of true. It specifies whether or not the line should be obscured by objects closer to the camera. Here we can see the result of calling the debug drawLine function. You will see that the start position is the origin in world space 0, 0, 0, and the end position is 3, 3, 0. The color of our line is blue, and it will be made visible for 30 seconds. As you can see, this will draw a blue line in Unity between the specified points, as shown in this screenshot. Let's jump to Unity and get some hands-on experience using this function. We will open up the example 3 resource attached to this lecture. If you look at the start function of the script, you will see that we call the debug drawLine function and pass in 4 arguments. We have a start point of the origin in world space 0, 0, 0, which is passed in as a vector 3, meaning an x, y, and z position. Then we will give it an endpoint of 1, 0, 0. Our line is going to be rendered blue since we passed in a color value. If we didn't specify a color value, then the line would be drawn as white. 60f is the duration that the line will be shown for. If we hit the play button in the editor, and then you pause the game and jump to the scene view, you will see the line. Note that you can only see this line in the scene view. And that's how you make use of the debug drawLine function when debugging your game. Debug break allows us to pause the execution of our code at any point. This function does not take any parameters. Here is a snapshot from the Unity documentation on this function. Important points to note are that it does the same thing as a breakpoint would, and it pauses code execution so that you can check the value of your variables. There is also an example of debug break being called here. Again, you will notice that this function doesn't take arguments. It is called with an empty set of parentheses. Here is some more information on the debug break function. It does the same thing as breakpoints. Also, we can put debug break statements all around our code if we want to. There is no limit to how many we can use. This function is great for situations where things happen so fast that it is hard to pause the editor in time to inspect the values. You definitely want debug break in your debugging toolkit. Let's jump to Unity and get some hands-on experience using debug break. We will go into the example 4 resource file attached to this lecture. In this case, we will use debug break to pause the editor if the ammo count is less than or equal to 90. This will require us to hit the spacebar twice, since 5 is subtracted from the ammo count each time the spacebar is hit. Let's hit play in the Unity editor to see this in action. Note that once the debug break statement was hit, the editor was paused. In situations where you want to pause the editor in certain conditions when debugging, this function can become quite useful. A null reference exception occurs if you try to use a reference variable that isn't referencing any object. The object that you are trying to reference is null. There are several possible causes of a null reference exception. You may be trying to access an object that is null. The variable is in your script, but it isn't referencing anything. You could also be trying to access an object that doesn't exist at all. Another possibility is that the variable does not reference an object at some point in your code. There are many possible solutions to a null reference exception, and each varies on what the cause of the null reference exception you are dealing with is. First, you can use the line number in the stack trace to discover where or why the value isn't referencing an object and make it reference an object. Also, you could add in code to check that the variable is not null before referencing it. For example, if GameObject does not equal null, then do the following. Alternatively, you can use a try-catch block to try to use the variable and then catch the exception if it is thrown. Let's jump to Unity to get some hands-on experience debugging a null reference exception. We will open up the example 5 resource file attached to this lecture. If you hit the play button in the Unity editor, you will notice that a null reference exception appears in the console. We first look at the stack trace to see the line number where the error is occurring. If you open the script, you will notice that we are using GameObjectFind to look for an object named player, but no object named player currently exists in our scene hierarchy. We could create a player object in our scene, and that would fix the issue, as long as we spelled the name of our game object exactly as it is typed in the script. Alternatively, we could put in some defensive code to guard against a null reference exception. Defensive code is code that we write to add some extra safety and ensure that we do our best to write safe code with the least possibility of throwing an error. We could wrap our code in an if statement to first check if our game object obj is null before we do anything with it, as I am doing here. Alternatively, we could use a try-catch block to try using the game object and catching the null reference exception if it occurs. We call the potentially error-throwing line in the try block, and then add a catch block right after it, with the name of the error as a parameter, and then optionally do some logic in the catch block to handle the error gracefully. An index out of range exception occurs when an argument is outside of the range of values allowed by the method. Here are some possible causes of an index out of range exception. You may have an array or list, and you are trying to reference an index that is too large. Remember that indexing starts at 0, so an array of length 3, for example, has valid indices 0, 1, and 2. Also, your array or list may be empty, but you are trying to access an element in it anyway. Finally, you may be using less than or equal to, or greater than or equal to, and it is iterating n times instead of n-1 times. In other words, if the list has 5 elements, and you are using a for loop with the condition that an integer x starts at 0 and increments by 1 until x is less than or equal to the length of the list. The problem is that the length of the list is 5, but only indices n-1, or 0 through 4, exist in a list that has 5 elements. Here's the approach at fixing an index out of range exception. First, see if you can quickly spot the error by looking at the list or array in question and the indices that you are referencing. Next, see if you are using the less than or equal to or greater than or equal to symbol, and see if changing it to less than or greater than fixes your issue. Finally, you can print out the length of the list or array in question, and to make sure that all of the references to indices are within the valid range 0 to n-1. N is just the length of the list or array. Let's jump to Unity and take a look at how to fix this type of error hands-on. We will go in the example 6 resource file attached to this lecture. When you hit play, you will notice that an index out of range exception was thrown. As you can see, we have a game object array and 4 game objects. In the start function, we are creating a new game object array of length 3, and then we are assigning these objects using the indices in the array. Did you spot the error? Our array is length 3, but we added 4 elements to it. The valid range of indices for this array is 0 to 2, and therefore we cannot add an element at index 3, like we are trying to do here. To fix the error in this case, we could change the array to be length 4 instead of length 3, which would work. Now if we save our changes and hit the play button, an index out of range exception is no longer thrown. Unexpected symbol blank in class, struct, or interface member declaration means that the compiler found a symbol that didn't belong at the place it is in the code. The following are possible causes of this error. You have an unfinished line in your code, you have an extra opening or closing parenthesis or bracket, You forgot a semicolon at the end of one of your lines. You have a return statement outside of a function. You forgot a type declaration before your variable assignment. Possible solutions to this error are to check to make sure that each line of code is finished and ends with a semicolon. Make sure each opening parenthesis or bracket is matched with a closing parenthesis or bracket. Make sure that any return statements are inside of the function bodies they belong in. And make sure each variable assignment has a type declaration as well. Let's jump to Unity to get hands-on experience fixing this type of error. Open up the scene and script in the example 7 resource file attached to this lecture. We will uncomment the return line and save our script. In Unity, we will see that we get 2 errors: unexpected symbol return in class, struct, or interface member declaration, and unexpected symbol semicolon in class, struct, or interface member declaration. Sometimes you will get multiple errors in your project, and you will want to tackle them one by one, usually starting with the error at the top. Our topmost error tells us that the symbol return is unexpected. When we look at where our return statement is, you will realize that it isn't inside of any of our functions. Also, all of our functions return void. To fix this issue, either get rid of this unused return statement, or put it inside of the calculate damage function and change the return type of the function to int. Once we do one of these solutions and save our script, you will see that this fixes both of our errors. We always solve our errors one by one, because sometimes fixing one will fix some of the other errors that the compiler is throwing. In the next lecture, we will look at an overview of the video game project that we will create in this section of the course.